Okay, so in this second video of surface area, we're going to talk about curves that are represented by parametrization. And so we can also find the surface area if the curve is defined using these parametrics. So let's say a curve is parametrized as x equal f of t, y equals g of t, as t goes from A to B. Okay, so as long as this range for t traverses the curve exactly once, then the areas of the surfaces generated by revolving the curve about the axis are as follows. If you revolve the curve about the y-axis, I'm sorry, why did I say y-axis? If you revolve the curve about the x-axis, where y is greater than or equal to 0, then the curve would be the integral from A to B, where t goes from A to B, 2 pi times y times the square root of the derivative of x with respect to t quantity squared plus the derivative of y with respect to t quantity squared dt. And that would be the same as saying, another way to say that would be 2 pi times y times the square root of x prime quantity squared plus y prime quantity squared dt. You just have to know when we say x prime and y prime here, we're differentiating these with respect to t. Now, to revolve about the y-axis, it's actually going to be that the surface area integrating from as t goes from A to B, 2 pi x, but then you still use the same square root expression here. So, and then another way to write it is 2 pi x times, again, the same square root expression that I used up here. Okay, so these are formulas that you can use to find the surface area when the curve is parametrized using the variable t. Alright, so let's talk about what if our curve was a circle of radius 1 centered at the point 0, 1. Okay, so here's the circle right here that I'm talking about. Now, the way we would parametrize that circle would be x equal cosine t and y equals 1 plus sine t. And to get the entire circle, t would have to go from 0 to 2 pi. Now, what if I sweep this circle around the x-axis? Okay, now I kind of cheated here, and I think I used Wolfram Alpha to get this picture. But if this is kind of the picture you would have, this is the picture of the surface that you would have if you revolve that circle about the x-axis. So it kind of looks like a tire, but it really doesn't have a hole in it here. Okay, so now using the parametrization formulas that we just talked about, we know that s about the x-axis, we would integrate 2py and then times the square root of x prime squared plus y prime squared dt. Now, we know that t goes from 0 to 2 pi, so that's going to be our limits of integration, because it takes 0 to 2 pi to draw this curve one time. So that covers that. And then we bring down the 2 pi, and then y in the parametrized form is actually 1 plus sine t, so we have 1 plus sine t. And now let me show you what happens here when you do x prime. If you take the derivative of x here with respect to t, if you take the derivative of x with respect to t, you get minus sine t. And if you take the derivative of y here with respect to t, you get cosine t. And now let's go ahead and do this calculation here. X prime squared plus y prime squared would be sine squared plus cosine squared, and then that would just give me 1. So really, all I have in the radical here is 1. So I just have square root of 1. So this is actually going to work out fairly nice. I can factor the 2 pi out of the integral, and then I have 1 plus sine t dt. And so if you integrate 1 plus sine t dt, you'll actually get t minus cosine t from 0 to 2 pi. And then if you evaluate that from 2 pi, I'll leave the 2 pi on the outside for now and just evaluate the t minus cosine t. So if I plug 2 pi in here, I get 2 pi minus cosine 2 pi. And then I'll get, if I plug in 0, I'll get 0 minus cosine 0. So here I'm going to get 2 pi minus 1. And then here I'm going to have minus a negative 1. So I actually have, it looks like I have, okay, the minus 1 and the plus 1 cancel. So what I end up with is just 2 pi times 2 pi, which is 4 pi squared. And so that's the surface area from that revolution. This just shows you another way you can write these equations. So here you can actually call this portion of this integral, you can actually just call it ds. So if you let that be ds, and then for this one, this would actually be the ds there. So anyway, that's the formula that you can do. Just another way to write the formula. And if you think about it, what both integrals have is both integrals are in the form of 2 pi times the radius of the solid of revolution, and then times the bandwidth of the solid. And so if you treat this Greek letter rho as the radius from the axis of revolution, and then you say it has an arc length of ds, then this becomes just 2 pi times rho times ds. It's kind of just another way to write it, but actually I'll show you how you can apply that formula in the next example though. So in this example, we want to find the area of the surface generated by the curve y equals x cubed, and from 0 to 1 about the x-axis. So here's the curve y equals x cubed from 0 to 1. Here's 0, and obviously this would be 1. And then if you revolve this around the x-axis, you kind of get a horn here, like there. So what you're trying to do is you're trying to get the surface area of that horn. So to apply these formulas here, I'm going to first of all find, I know that the curve is y equals x cubed, and then I know that dy is actually 3x squared dx. So when I calculate this ds here, and this is the ds, so I take dx squared plus dy squared. Well, dx squared would just be dx squared, but when I square dy, I would square this. And so when I square that, I'll get 9x to the 4th, and then I'll have dx squared. So let me go ahead and just factor the dx squared out of these two terms. So factor that out, and you get dx squared factored out of the first term gives you 1. And if you factor the dx out of the 9x to the 4th, you'll just get 9x to the 4th. There. So we factored the dx squared out of those terms. And then, since that's dx squared, if we take it out of the radical, we'll just get a dx on the outside. So now, going back to the formula that I need the 2 pi times the radius. Well, the radius would be the distance from here to here. So the distance from here up to here would just be the y value, which is x cubed. So I'll put the x cubed in there, and then of course I also need the length of the arc, which is actually where this comes in. So this is the length of the arc, and then I'm going to integrate that arc from 0 to 1. I'm going to integrate it from x equals 0 out to x equals 1. And so here, let's see what I get here. So what I did here is I'm going to use a u substitution to do this integral. So if I let u equal 1 plus 9x to the 4th, then du would be 36x cubed. Okay, so I didn't show you that work. I'll go ahead and stop the video and try to put that in there for you so you can see the substitution. Okay, so let me show you what I did here. Factor the 2 pi out, and then I'll need a 36 in here so that I'll have 36x cubed and the dx. So the 36x cubed and the dx, that'll give me du. So there's where I got the du. And then since I'm letting u be what's in this square root, I just didn't write it, but this would be u to the 1/2. So this up here would be u to the 1/2. So that's what that says, u to the 1/2. So I actually end up with an integral of u to the 1/2 du. Now, I know it says 0 to 1, but right here, since I'm doing it in terms of u, plug 0 in for x here, and you get u equal 1, and then plug 1 in for x, and you get u equal 10. So in terms of u, the limits of the integral would be from 1 to 10. Okay, so then if you integrate that, you get u to the 3/2 times 2/3, and now 2 pi over 36 reduces to pi over 18, and if you multiply that by 2/3, you get pi over 27, and then you have to evaluate u to the 3/2 from 1 to 10, so that would be 10 to the 3/2 minus 1 to the 3/2, which is just 10 to the 3/2 minus 1, and then times pi over 27. So there's the value of the surface area of that horn that we generated. Okay, pause the video and just go ahead and read what I highlighted in blue here. And so it just talks about why we don't use cylindrical bands instead of conical bands. But you can read that. So it's just a little bit of a caution for you that I threw in there. So anyway, pause it and then read it and then move on. Okay, a guy named Pappas actually discovered 2 formulas that relate centroids to surfaces and solids of revolution. The formulas actually provide shortcuts to a number of lengthy calculations. So Pappas discovered that if a plane region is revolved once about a line in the plane that does not cut through the region's interior, then the volume of the solid it generates is equal to the region's area times the distance traveled by the region's centroid during the revolution. If rho is the distance from the axis of revolution to the centroid, then the volume is simply 2 pi times rho times the area. Okay, so this torus is actually generated by taking a circle and revolving it around an axis, and you get this torus here. So the volume of this torus can be calculated using this formula, where you have the volume is equal to 2 pi and then times the distance that the centroid is from the center. So we're going to just say that's b, and then times the area of the circle, which is pi a squared, where a is the radius of the circle. So the volume of the centroid is actually 2 pi squared times b a squared, where a is the radius of the circle, and then b is the distance from the center to the centroid of the solid. Okay, I didn't give you the whole picture. There's actually some information down here that helps you understand that problem. I don't have time to finish these last 2 pieces, so I'm just going to show them to you. So go ahead and freeze the video and you can read it. On this example, we're using Pappas's theorem because we can get the volume, and from the volume of that we can get rho, and then using rho we can actually get the centroid of the region generated by that solid. And then I'll leave you with Pappas's second theorem for surface areas. And again, I don't have time to do this justice, but go ahead and just read that theorem, and then read the observation that I made for the surface area of the torus there. And hopefully, there's enough there for you to understand, but I didn't really want to do another video on this just to finish up this theorem. So that pretty much completes the section on surface area of revolution. And in the next section, we're going to deal with work problems and work